Okay, so welcome everyone to Guided Study Group Week 3 of Math 140. So hope everyone have a great week since last time, and we're now ready for the next materials from section 2.5 to 2.8. So we have a lot of things to cover today, but most of the thing I look through your lecture notes, I feel like it's really thorough and detailed already, so I wouldn't repeat so many things, just list out the main points. And if you have any questions, feel free to refer back to the lecture notes. And okay, let's get started. So in 2.5, today we're going to cover 2.5 and 2.8, by the way. So in 2.5, first of all, we have things like composite function. So kind of like introduce you to this kind of notation that will actually just means that you take another function out of the original function. Say you have gx, and then you just take f of whatever value at that gx is. Then we have chain rule. Chain rule is basically allow us to take derivative of any kind of functions that the variable is not just simply x. So say if you have square root of sine x, so obviously the variable here under the square root is sine x and not just x. So what you got are things like you have y squared plus 1 over 2y minus 4 to the fourth. So now if you want to take derivative of this thing inside is not simply just y, it's a fraction. So you have what additional step that you can take is that you have to multiply the extra derivative of whatever inside that function. So say here instead of y to the fourth, you have y squared plus 1 over 2y minus 4. So you have to take that extra derivative of y squared plus 1 over 2y minus 4. So take that extra derivative of that fraction. Last, so I say it's kind of overlap with the thing that I'm about to say is the power rule combined with chain rule. So that's when you have, say here, you have u to the n, with u is a function of x. So when you take derivative of that, it's going to be the regular way that you take x to the n is that you're going to have n multiply u to the n minus 1. But then the extra thing is that you multiply what's the derivative of u with respect to x. And we're going to see that, I think you have seen that in the lecture notes and also in the rest of the example. So our example is just going to cover some of the main points, some of the special type of exercise that you must know in order to like actually say, okay, I understand the main points of these sections. Then we also have quotient rule combined with chain rule. So again, as we said, say if we have f equal is a function of x, f is a function of hx. So then if you have f over g and you try to take derivative of that, you're going to have g squared down here. You have f prime g minus g prime f. Now, f prime is not just, it's going to be f prime of hx. Then because of chain rule, you have to multiply h prime of x as well. Multiply g minus g prime f. And then you have g squared. So this is the additional thing when it comes to quotient rule combined with chain rule. It's just the h prime x that you have to multiply. Then we have, so let's start it with the first example. So the first example, since we have here, is find the derivative of this fraction to the fifth. So first of all, as I say, we have so let's take let's call this thing u. So you have 5 u fourth multiply u prime. What is u prime? Okay, this is pretty bad and not u. Let's put it t. Then it should be t fourth multiply t prime. So now we have what is t prime with respect to y. So then we have y fourth plus 1 over y squared plus 1. Now take derivative of that. So now is where we're going to use quotient rule. So it's helpful in a sense that when you are not used to combine a lot of things together. Okay. Kind of I start at the time. So do you want me to go over like what I just started, or should I just continue what I'm doing? Also, yeah, please put your PSU email in the chat room, please. So I'm just gonna continue with what I'm doing here. So basically, we're solving the first example where we try to use chain rule and product rule and quotient rule. So here we have a fraction to the fifth. So we're just gonna take first its derivative with treat this fraction as a variable t. Then you're gonna have derivative of this entire thing to the fifth. It's gonna equal 5t to the fourth multiply t prime, and we're on the way to use quotient rule to figure out what t prime is. So we have, and then we have y squared, or we have y fourth plus 1 multiply 2y. Okay, Michael, can you hear me? Because it looks like you just drop out and then come back. So please put your PSU email in the chat room and we'll continue to do what we're doing here. So we're just trying to find combined chain rule and quotient rule together. But here we have a fraction to the fifth. So again, it's going to be equal 5t fourth multiply t with t is the inner fraction. And we're trying to find what is t prime. This is very helpful. This extra step is helpful for when you just started with this chain rule, because it's gonna make us easier to keep track of what we're doing. 2y fifth minus 2y divided by y squared plus 1 squared. So what we have here is we have y squared plus 1 squared, and I'm having 2y fifth minus 4y cubed minus 2y. And therefore we have u prime with respect to y is going to be 5 multiply y fourth plus 1 over y squared plus 1 to the fourth multiply this thing as well. So there's going to be another 2. I take all the 2 in the numerator out. Y fifth plus 2y cubed minus y squared plus 1 square. If you want to further simplify this, what you end up having is going to be divided by y squared plus. Okay. Any questions so far? Okay. Yeah, it looks like you just drop out of the sessions again. I guess it's the internet connection. But anyway, when you rewatch the videos, you guys gonna see how do we end up having to over here when we take derivative. So this is just if you feel that it's too fast or you don't understand what I'm saying, please email me or like stop me at any time if you join me online. Unfortunately, there's no one here right now, so I'm just gonna be by myself and working on this. So but that is the answer, and the key here is just basically know how to use chain rule. So chain rule here is when I put the inner fraction as a value t, and t here is a function of y. Therefore, when you take derivative of t to the fifth, then you have to multiply t prime as well, and this is t prime, this extra step. So that's example 1. Now we're going to go to example 2. Similarly, but this one is more a little bit numerical, when you're given some values and it's asking you to find what's h prime of 1. Now, given the relationship between h and f, kind of like h is the square root of some function of f. So let's use chain rule to just break it down first before dealing with the numbers. So here, the outer function is square root. So it's kind of like taking the derivative of 3 this to the half, and then this entire thing, you take derivative of this. So it's equal, take the half out, you're going to have 4 plus 3 fx to the negative half, multiply. What is the derivative of 4 plus 3 fx? Now this derivative is going to be, yeah, let me write it down again to not confuse any of you by going too fast. Again, if it's confusing, let me know. I will adjust my speed because I tend to go really fast if there's no one joining me. I will assume people understand. But then, so here we have, what is derivative of 4 plus 3fx? It's just going to be 3f prime of x. Because derivative of 4 is 0. And if you have a constant, multiply a function, you try to take derivative of that, take the constant out and multiply the derivative of that function. Now we have is 3 half multiply 4 plus 3fx in the square root because it's to the power of negative half. And then you have f prime of x. Now, if we want to find h prime of 1, basically we're just going to plug everything related to x into 1. So you have f prime of 1 divided by square root 4 plus 3f1. Therefore, now what we end up having is 3 half multiply f prime of 1 is 4 as given, divided by square root 4 plus 3 multiply 7. So what we have is now this with this is going to be 2, cancel out. We have 6 over square root of 25, which is going to be 6 over 5. So this is the answer. Obviously, first of all, you shouldn't look at these numerical at all and just look at what you have to find and just go slowly. When you write them all down and make sure that every step is correct, you're just going to see the fact that they just give us barely enough information to solve the problem. So don't let the numbers confuse you. Just look at what is given, like the main part, and then look at what they're asking. If you have no idea what to do with the number at first, just ignore it. Because as you write the things down, like here, you're going to see the relationship. Now that's 2.5. Really easy. Chain rule is quite obvious to someone who already took calculus in high school, but that's not the general case of this class. So I would assume that everyone will have some problem with it, and I hope my example helps. If not, again, let me know or look at the lecture's notes again, because this has a lot of examples that will clarify what we're saying. And Dr. Kasha obviously goes slower than I am to make sure that you guys understand the materials. Now, it's coming from 2.6. So 2.6 is about implicit differentiation. This is a very important section when you guys continue to deal with math 230, where we 230 to 231 or 232, where we actually deal with multivariable curve and 3D and 4D, those stuff. So, but even though if it's not in in math 141, it's still important as well when we're dealing with log differentiation. So the application of implicit differentiation is it's just a way to take derivative of those kind of functions that cannot be written as y equal to fx. So say things like a circle, like you have x squared plus y squared equal 25 with, or like 5 squared, this is a function of a circle. Or you have things like x squared over a squared minus y squared over b squared equals something. This is a hyperbola. Or if it's graphically, it's going to be some function that when you draw it out, say like a circle, one value of x can give you two value of y, or like an ellipse or hyperbola, it doesn't really matter. One value of x give more than one value of y, then that's the function that you're going to use implicit differentiation if you want to find derivative. Now the step to do that is that first we consider that function and treat x as the independent variable. So basically if you have x squared plus y squared equal 25, for example, then you're going to have, if you take derivative, you're going to have 2x multiply dx over dx plus 2y dy over dx. And then 25 with respect to x is going to be 0. Now this part is equal to 1. dx over dx is 1. But dy over dx is not 1, it's y prime. And you have to keep that, and it's not 1, so you cannot just cancel it out. And yeah, take derivative of both sides with respect to x. And take whatever related to y prime. So here you have I will cancel out the 2 as well. So just what we have now is x plus y multiplied y prime equals 0. And if you take y prime out and everything not related to y prime on the other side, you're going to have negative x over y. You take this x over here, and then you have negative x divided by y. So the step is pretty easy, but you have to always remember the fact that when you take any kind of derivative, when you see dy over dx, do not cancel it out, because just one variable can screw your entire answer up, because it tends to be a little bit complicated with the final expression. Like it's kind of like algebra, very algebraic involved, but the general idea is that you cannot ignore dy over dx because y is a function of x. Now we have example 3. Let's try to apply what we just reviewed. Use implicit differentiation to find equation of a tangent line to this curve. Now, again, as I told you last week, I will always ask you what is the general function of a tangent line. So a tangent line is going to have y equal y prime at x0, which is given as pi, x minus x0 plus y0. x0 and y0 is the coordinates, which is pi and pi here as given. Now, all we have left is just y prime at pi, so we have to find y prime first, so that you can plug pi in. So we have find y prime. And to do that, given this function, obviously you cannot just write y equals something of x, because you have sine here as a trig function and you have polynomial, so it's very complicated and there's almost no ways I can think of that you can separate them. But then we have to use implicit differentiation. So first we have to take derivative of both sides with respect to x. Then you're gonna have cosine of x plus y multiply whatever is derivative of x plus y equal to x 2 dx over x is going to be just 1 multiply 2y prime. Now we have cosine of x plus y. Derivative of this thing here is 1 plus y prime, because derivative of x with respect to x is 1 and derivative of y with respect to x is y prime. So you have 2 minus 2y prime. Now we want to find y prime, so we have to take everything with respect to y prime out. So you're going to distribute here. You're going to have cosine x plus y prime multiply cosine x plus y equal to minus 2y prime. Or if we take anything related to y prime on one side, we're going to have 2 plus cosine x plus y equal to 2 minus cosine x plus y. And we end up having y prime equal 2 minus cosine x plus y divided by cosine 2 plus cosine x plus y. And so now we just need to plug it. So when you have y prime at pi, you plug x and y be pi and pi, the two coordinates given. 2 minus cosine 2 pi divided by 2 plus cosine 2 pi. So what we have is going to be 1 over 3. Therefore, we have the tangent line become 1/3 x minus pi plus pi, which is going to be 1/3 x plus 2 over 3 pi. So this is the simplest form that we can get. So basically the hardest step is use implicit differentiation to find these stuff, but it shouldn't be too hard. Consider the fact that you already look at the lecture notes and kind of like understand at least 60% of the implicit differentiation. So that is example 3. I go a little bit too fast here because it's kind of like simple, but let's see what's going on in example 4. So example 4 is question 27 of your book, and it's given this curve. Find equation of a tangent line again. So the step, as we just said, I don't want to mention the general equation of a tangent line just for the sake of space. I don't have much space here. But for A, tangent line, again, what we're only missing is that we have the x naught and y naught. We're only missing y prime at x naught. So we're going to have y squared equal x cubed plus 3x squared. Now, if you take derivative of both sides with respect to x, you're going to have 2y dy over dx. 3x squared multiply dx over dx is just 1 plus 6x. Now we're going to have y prime equal 3x squared plus 6x divided by 2y. And you just plug 1 and negative 2 in. So we have 3 plus 6 divided by negative 4, which is negative 9 over 4. So you're going to have tangent line be y equal negative 9 over 4. Let me know if I make any calculations mistake as you look through this. So we have negative 9 over 4x plus 1 over 4. Because it's plus 9 over 4 minus 2. So it's going to be, this is the answer with a negative here. Remember. Let me make this easier to see. Okay. Now, that is question A. Not too hard, kind of the same thing when we use implicit differentiation and just plug it into the tangent line. Now, it's asking at what points does this curve have horizontal tangents. So basically, you have to solve for when you have y prime equals 0. Because here, with the tangent line, y prime at x naught is the slope of the tangent line, and so you have to keep it equal 0 to have that. So now we're gonna have 3x squared plus 6x over 2y equal to 0. In other words, we have 3x cubed plus 6x equal to 0, but y have to be different from 0. Why is this the case? As I'm saying here, if you want the entire fraction to have a value, and that value is equal to 0, first of all, the denominator have to be different from 0. That's why we have this condition. Because it has to be different from 0 so that the fraction has a definite value, which is a number, and here is equal to 0. Therefore, we're going to solve, and we're going to have x equals 0 or x equal negative 2. And y have to be different from 0. Now, at x equal to 0, when you plug it here, you're going to have y equal to 0. As given in this equation 1. When x is equal negative 2, y is going to equal negative a plus 12, so it's 4. Now, for sure, this answer is wrong, x equals 0 at y equals 0, because your y for condition is different from 0. Therefore, you only have one value left, which is x equal negative 2 and y equal to 4. So this is the answer at negative 2 and 4. The tangent is horizontal. So basically, all of these exercises kind of like practicing you guys to the point that, okay, figure out what the problem gives us in the problem statement and what they're asking for without looking at the answer choices yet. And I think it's a really good practice for your exam because you're gonna have a practice problems like multiple choice questions, and then if you just look at the answer and not actually think about how to go, like which step to go and what you're gonna write down, it's never gonna help you understand the materials at all. Having said that, I don't need this extra space. Wow. So this is kind of like the graph when I graph that function out. So this is the function. This is the function, the whatever Tinhausen equation or something. But then these are the two horizontal that we have. Two horizontal axis tangent that we have. So the first tangent is here in the question A. And then we have, hang on, am I missing something here? Because I do have a feeling that I missed something, but I'm not 100% sure. Give me a second. I'll check back with my note. It's 2.6. So you're gonna have Oh, here you have y squared is equal to 4. But then you're going to have y equal to 2 or negative 2. So which is going to be the 2 points here? So I'm like, why do you have 2 points? Because no answer. I'm sorry, it's just y squared equal to 4. So you're going to have 2 value of y, which is 2 and plus 2. 2 and negative 2. So this is the 2 points that we found it had horizontal tangent. It's clearly seen on the graph. Now, I think it's pretty clear when we come to this. Now it's just 2.7, application of derivative. So in this section, there's no new materials at all. It's all talking about the meaning of derivative, which I kind of like go through briefly last week when we talk about, okay, what is the meaning of that, and like triographic meaning of triography, graphical meaning of derivative, and kind of like the physical meaning as well. So when we have kind of like delta y over delta x, so the change of y over the change of x is called average rate of change. But when you take that interval of delta x to be really, really small, that should be delta x going to 0, then you're going to have that become the instantaneous rate of change. And it's also equal to the derivative of y with respect to x. So some of the problem that you can be given in this question, as I see in your lecture notes, you have one is related to kinematics, and the rest is kind of similar, but by all means, it also have application in other fields, like I think Dr. Kasha mentioned marginal cost, marginal revenue, marginal profit, and even like heat flow, rate of heat flow, any kind of related to rate, like reaction rate or rate of heat transfer, or like rate of energy, rate of reaching equilibrium in chemistry, or like even rate of growth in biology, those kind of stuff. So say if you're given S as the in physics and kinematics, if you're given S as the position function, derivative of S is going to be instantaneous velocity, and derivative of velocity, or the second derivative of S, is going to be acceleration. So that's kind of like a very old derivation that I don't want to spend time talking on, but this is kind of like the main thing that you have to care about in these sessions. So here we have, for example, in this section is example 5. It's just very simple, similar to one of the examples that Dr. Kasha did. So I just mentioned it here because the entire point of this is just go through the main problems that you guys must know for kind of like surviving this class. So we have a particle move giving this function. T is measured in seconds. What is the velocity at time t? So again, we just say that velocity is the first derivative of s. So it's going to be 3t squared minus 18t plus 24. Now, what is the B is going asking, what is the velocity after 1 second? So you just plug in what is velocity at 1. So you're going to have 3 minus 18 plus 24, which is going to be 27 minus 18 is 9 meter per second. Feet per second. Because x is in, this is s, not x. Dang. Shame, this is s. Okay. Now, that's very simple. Next one is where it's asking us to find when is the particle at rest. So when you have velocity equal to 0, then the thing is not moving. The object is not moving. Therefore, you have to solve for what is Vt equals 0. Or you have 3t squared minus 18t plus 24 equal to 0. And if you solve for it, I will simplify this thing first. And you're going to have t minus 3 squared equal to 1. Because this thing, if I rewrite it, I will just go slowly here because it might be a little bit confusing. Or you can just use like the regular delta a and b to solve a quadratic function here. But one of the way that I usually use, because the way that I was teach math is that you need to know how to do a lot of manipulation to kind of like make your life simpler. So you're gonna have, yeah, just like write as plus 9 minus 1 and move the 1 over there. Take the 1 over there. And this is complete the square. And this 1 is over. So what we end up having is that t equal to 4 and t equal to 2. So the particle runs from 0 to 2 seconds, and then it stopped, and it do something in between, and then it stopped again at 4 before moving again. Now, it's asking, D is asking when is the particle moving in a positive direction. Now, you have look about this. Here we stop twice, but you have no idea what's going on in the middle. Like, they can go backward, they can just go forward again, or they can go, or they just stay there. Oh no, actually not stay there. They can go in both directions, back and forth. So what we have to figure out is on what interval that the velocity is positive. That's because the velocity is given usually under the assumptions. I'm not talking about math right now, but in physics, they usually give the velocity with respect to the positive direction that they chose in that kind of system. And so basically you're just gonna solve for what v is bigger, what value of t is gonna be give v bigger than 0. You solve for this, or we have t squared minus 6t plus 8 bigger than 0. Ooh. Dang, just bigger than 0? Okay, bigger than 0. Now, if you solve for this in the, say, let's put it in a table. So we solve for it, and we found the 2 interval that it is equal to 0. Now, let's plug in some values in between and see what is the sign there. So if we put in 1 here, have 1 minus 6 plus 8, so it's a positive. And then from 2 to 4, if you plug in 3, 9 minus 18 plus 8 is a negative 1. So, and then you plug 5 in, so you have 25 minus 30 plus 8, so it's a positive. Therefore, we're going to conclude that. What just happened? And we can start a slideshow again. Don't worry. So here we have, oh, so here we have from 0 to the second to 2 seconds, and from the 4th second, the particle is moving in the positive direction. Now, we have 2 of these with a positive direction. And so what happened is that from now for E and F is asking us to find, and I will actually continue, that's the continue of the point from D, is to find the total distance traveled during the first 6 seconds and draw a diagram to show the motion. I think it's better if we just draw a diagram first. So we have from 0 to 2, the object is moving to the positive direction. Let's do this, the positive direction. And then let's go back something. And then at 4, let's go positive again. Now we have to find what is the distance from that the object travel. And obviously you can see that you cannot just take s at 6 minus s at 0 because there's some overlapping here as the object move back and then move forward again. So the actual distance is going to be much bigger than s6 minus s0. So I would say distance travel is not equal to s6 minus s0, even though a lot of people just like, why is she doing all of this, and it just takes so much time, why don't we just do that? Oh, actually it's the wrong answer. So just trying to show you guys that that's the thing. Now we're gonna figure out, so The distance traveled is equal to S2 minus S0 first. This is the first part. Then you have S2 minus S4 on this page because you're going backward. So the distance is going to be from here minus here. And then you have S6 minus S4. Because now it's come back to the positive direction. Now S of 2, so we have S function is going to be t cubed minus 9t squared plus 24t. T cubed minus 9t squared plus 24t. Now if we just plug into 0, 4, and 6, so I'm not going to do the algebra here, because yeah, I just plugged them all into the calculator, which is should not be the case, but I actually did. So what we have is gonna have 44 feet total. So this one you should have 20 feet, this one you have 4, this one you have 20, and total is 44 feet. And obviously you can compare with the answer of S6 minus S0. If you I did the plug-in, so we have it's gonna be 36 minus 0, which is just 36 feet, and you missing that 8 feet. So these are definitely different, and this is gonna be the way to solve it. If you try to use S6 minus S0, you have to make sure that your particle only move in one direction. Here it go positive, it's go back to negative, and then go positive again. So the situation become a little bit more complicated. Now the last questions, 2. Find the acceleration at time t and graph those three position, velocity, and acceleration from 0 to 6. When is the particle speeding up or slowing down? And I think H is going to be answer based on the graph. So let's say we have Vt is 3t squared minus 18t plus 24. So AT acceleration is the first derivative of velocity, which is going to be 60 minus 18. Now we're going to graph it all three of S, A, and V on t cubed minus 9t squared plus 20 on one graph, and let's see how it works. So we have Vt is the red one. As you can see, it's all positive, and from 2 to 4 become negative again, and then it's go positive. And then we have St is t cubed minus 9t squared plus 24t is the blue line. And then we have At is just a straight line. Now to figure out where is it speeding up and slowing down. So the definition of speeding up is when you have velocity and acceleration with the same sign. So both of them are negative or both of them are positive. And then different for slowing down is that V and A with different signs. So say one is positive and one is negative, but it will never be both of them both positive or both negative. So if you look at here, same sign is asking for where speeding up. I'll do the speeding up, and the rest is just gonna be slowing down. So here you can clearly see that from you just care about the red one and the green one. So from 2 to 3 seconds is speeding up because both of them are negative, so same side. Here one is positive, one is negative, so it's slow down. And then from 3 to 4, one is positive, one is negative again, so it's slow down. And from 4 onwards, red is above x-axis and green is also above red x-axis. Therefore, both of them are positive. So here is speeding up again. So this is speed, slow, speed, and then slow. So we have 3 intervals with different action. You first slow it down, and then speed it up again, and then slow it down, and then speed it up. So a little bit complicated, but that is the case when you just look at the graph, and it helps you solve a lot of mathematical expressions. Now that's all I have for 2.7. Now it's going to be the last section of today, which is 2.8. So 2.8 is where you have everything put in word problem and you have to try to solve. Put it in first, mathematical, try to understand it first. Yeah, the understanding is the most important. Then you put it in mathematical symbols, read the problem carefully, draw a diagram if possible, and I would highly recommend it. Let's put this very bold here. Highly recommend it. A lot of time of my previous student, they survive these sessions and actually do really well in 2.8. It's because I try to make them interact, like kind of like connect whatever the word problem is with the kind of like the actual pictures, like visualize it how it actually looks like in reality before you plugging in it. No, before you actually try to solve it. You have to be able to picture it out, draw a diagram. The drawing the diagram is gonna give you to the fact that you're gonna put every single information's given in the right mathematical symbols, because now you know what you have to do and you know how to assign them. And then next one is identify the key relationships. Again, it's kind of like already hidden in the diagram. If you draw a diagram and you'll be able to identify the quantities, you should be able to see the relationship that's technically the thing. Then we have solving the problems using derivative. Use chain rule if necessary, and I've seen more than one problem that you actually need chain rule, so definitely use that. And you have plug in the correct expression to find the design variable. Now, plug in the correct expression to find the design variable is where you have plug in the informations given in the right one and just kind of like solve the problem. Now let's start with, I have two examples here. It's actually the examples at the end of your lecture notes. So if you were struggling to solve it, because I don't think Dr. Kasha put the answer keys up there. But again, if you have some problem solving it, now is the time that we're going to go through it together. Or if you rewatch it, don't hesitate to just see like how I solve it. And if you have any further questions, email me and CC Dr. Kasha so we can help you as soon as possible. Now we have the street light is mounted at the top of a 15 tall pole. So this is a pole and you have light. And this thing is 15 feet. A man 6 feet tall is walking away from the pole with that. So this is the man and he is 6 feet. Now we have, this is the wall. So he's walking this way at 5 feet per second. How fast is the tip of his shadow moving? So now we're looking at these questions and it's asking what is the, let's redraw this thing. This is slightly slanted in a sense. So it's asking what is the velocity of this tip here. When you have this part is 40 feet. Now, if you just redraw it in, like make it easier to look like, you're gonna have, this is 6, this is 15, this is 40, and this thing is moving over here with 5, and it's asking what is the moving over here with the horizontal one, because this is the shadow that he has. So if we call this is X and the entire part be Y, then we're gonna have, this is the entire part. This is Y and this is X. Therefore, if you look at this, it's kind of like giving us a sense, sorry for the flipping of it. It's kind of giving us the similar triangle. So we have this kind of relation. We have Y over X, Y minus X over Y equal to 6 over 15. Because this small triangle is similar to the big one, so we can draw this ratio based on this their base, the ratio of their base, this and this is going to be the ratio of their height, because they're all right triangle as well. And it's going to be 2 over 5. They give you dx over dt equal 5, and it's plus 5 because it's moving away, and so that distance with the wall is going to be increasing. and you have x is equal to 40. They're asking us to find what is d of y minus x over dt, or this, what is the rate of this. Note that we're looking for the rate of change of y minus x. So this is the shadow. The shadow is only from this point to here. It's not the entire thing. So it can be a little complicated, but here we already have this, the key relationship. Therefore, if we take both derivative with respect to time now, so we have d of y minus x over dt is equal to 2 over 5 dy over dt. Now, very clearly, if you have d of y minus x, this one is equal to dy minus dx divided by dt. So you can resolve it here. You have 3 over 5 dy over dt is going to equal dx over dt. Just like doing the algebra between these two. Or you're going to have dy over dt equal to 5 divided by 3/5 is 25 over 3 feet per second. So the entire thing is moving forward with this speed. But it's not the shadow. The shadow is d of y minus x over dt, which is dy over dt minus dx over dt, which is going to give us 25 over 3 minus 5. It's going to be 10 over 3 feet per second. Now, there are multiple ways that you can interpret this thing. So, some people actually consider the rate of change of the shadow is the rate of change of the entire y. And that's depending on your physical interpretation of the scenario. Here, because I look at it as the shadow only have this much, this y or minus x. So the tip of the shadow is here, and you only care about the rate of change of the shadow. Now, a lot of people just say, okay, the tip of the shadow is out here, and it depends on the entire thing. So I would say in the exam, don't worry about such confusion to happen, because it's like a multiple choice question, so we're gonna make sure that we specify with you, or make sure that there's just only one case that you have to consider in the exam, so it's not gonna get this confusing and controversial. But yeah, that's the scenarios. So we're done with example 6, and now we'll only have one more example to go. So we have this is kind of like a very classic one. I have a few students coming in last semester for tutoring in person asking me these questions, and I feel like it troubles a lot of students. So let's start doing this. So we have Jim lives 3 miles east of State College. So this is Jim, and this is 3 mile. Now, at noon, he leaves his house and work at 2 miles per hour. And then we have Annie live 4 miles away from in the north, and at noon she also lived for north at 8 miles per hour, and this is Annie. It's asking calculate the rate at which the distance between the two people is moving. Now, this is the distance, and very clear here when you're just talking about north and west and north and east. There's a right triangle here, so you can see the fact that it's Pythagorean theorem. So if we call this thing x, and this is y, then you have xy, and then this is z, x squared plus y squared equals z squared by Pythagorean theorem. And we're looking for what is dz over dt, because z is the distance, so dz over dt is going to be the rate of change of the distance. Now, it's asking the rate of change when it's 1 p.m. So both of them already travel for an hour. So the actual graph is now become, this is still 2 miles per hour because they don't change their speed. But the distance here instead of 4 is going to be 4 plus 8. So whatever it travels in an hour, 4 plus 8 is 12, and this is 5. So it's 3 plus 2 is 5. So because it's already traveled at 1 p.m. If it's asking for the rate of change at noon, then that's a different story. Now we have, and this is SC. So if we have to take derivative of this with respect to t, so you have 2x dx over dt plus 2y dy over dt is equal to 2z dz over dt. I think I kind of like missed this one in the review C sheet, is that dx over dt. Here x is a function of t, y is a function of t. Anything else except for dt over dt is not 1, and you cannot cancel anything out. So it's kind of like distinguish it between the implicit differentiation and this part. Now we have everything we need. We delete the 2, then we're gonna have at this point 1 p.m. x is 5, y is 12. So you have 5 dx over dt. Yeah, let's see what they're given here as well. Dx over dt is increasing because it's increasing the speed of the value of x. So it's going to be plus 2. dy over dt is going to be 8. Again, it's increasing the distance between Anne and Jimmy and the State College. Therefore, we have 5 multiply 2 plus y is 12 multiply 8, and this one's going to have z. Z right here, you can easily use Pythagorean theorem to find it, and I got is 13 multiply, you can take all the 2, dz over dt. Now you can just use algebra to find what is dz over dt. And what I've got for this question is, let's look at it. I actually just put it in earlier today. So we have 96 plus 10 is 106 divided by 13. Yeah, so that is my final answer, feet per second. So nothing really bad in this example, just kind of like identify the key relationships and be careful here when it's 1 p.m. or 2 p.m. And you're going to see the fact that the rate of change of distance doesn't go linearly. So like at 2 p.m. it's going to blow up, or it can be lower than what you expect it if it's just take proportion to it. So again, this section 2.8 is hard and challenging if you don't quite understand every aspect of derivative, and that's completely fine. Just make sure that you do all of the practice problems, and also keep in touch with me and Dr. Kasha if you have any problems. I'm really glad that currently I receive a lot of email from the student trying to like asking me to explain why they get something wrong in the quiz, and I feel like that's really helpful when they actually check their quiz after they finish. That's a very good practice to make sure that you don't miss any mistake and understand everything in the exam. Now, if you don't have any more questions, I will stop the meeting here, and I'll see you guys next week. Please feel free to email me or ping me anytime you need any more appointment. See you guys.